In analytical laboratory, the hardness of water samples is measured by complexometric titration using ethylene diamine tetraacetic acid disodium salt dehydrate, commonly known as EDTA disodium salt. Here, EDTA anion forms coordinate covalent bonds with the metal ion present in the given water sample. This bonding results in formation of a large complex structure, commonly known as coordination compound. These ions or neutral molecules, which are Lewis bases and can form coordinate covalent bonds with a metal atom or ion, are known as ligands. The number of ligands directly bonded to the central metal atom or ion is known as its coordination number. On the basis of the number of donor atoms present in a ligand, they are classified as monodentate, bidentate, polydentate, and ambidentate ligands. Monodentate ligands. To understand the monodentate ligand, consider hexa-aqua cobalt. Here, the water molecule is a neutral ligand. We know that the oxygen atom present in water is covalently bonded to two hydrogen atoms, while two lone pair of electrons are left unshared. When this water molecule approaches a cobalt ion, it donates one of these lone pairs of electrons to the cobalt ion and forms a coordinate covalent bond. As only one donor atom is involved in the formation of a single coordinate covalent bond, water is called a monodentate ligand. In this manner, a total of 6 water molecules get bonded to the cobalt ion, forming 6 coordinate covalent bonds. As cobalt ion is surrounded by 6 water molecules, the coordination number of cobalt in this compound is 6. In general, a ligand that can bind to a central metal atom or an ion through a single donor atom, forming a single coordinate covalent bond with it, is called a monodentate ligand. Bidentate ligands. Now consider a molecule of ethylene diamine. 2 nitrogen atoms present in this molecule form 2 coordinate covalent bonds with the central metal atom. Such a ligand that binds through 2 donor atoms is called a bidentate ligand. Polydentate ligands. Ligands that are capable of simultaneously binding metal ions through more than 2 donor atoms are called polydentate ligands. For example, diethylene triamine with 3 donor donor atoms is an example of tridentate ligand. The anion of ethylene diamine tetraacetic acid, which has 6 donor atoms or binding sites, is another example of a polydentate ligand. It can bind to a metal through 2 nitrogen and 4 oxygen atoms and hence is called a hexadentate ligand. You can see here that as the polydentate ligands appear to wrap the metal between the donor atoms, they are known as chelating agents. In general, chelating ligands form more stable complexes than the related monodentate ligands. For this, consider a molecule of ethane 1,2-diamine. Here, each ethylene diamine molecule is bound to the metal ion through 2 coordinate bonds, and thus the metal ion is surrounded by a total of 6 coordinate bonds arising out of 3 such ligand molecules. Such a large complex ion is much more stable than the hexaamine metal ion, in which the metal is surrounded by monodentate ligands, each providing only 1 pair of electrons. Ambidentate ligands. This is another class of ligands called ambidentate ligands, which, just like polydentate ligands, bind with metal atom or ion through more than 1 donor atom. However, unlike polydentate ligands, they do not simultaneously bind with the same metal ion. Thiocyanate ion is an example of one such ligand. It can form a coordinate bond with the metal ion through either nitrogen or sulfur, but not at the same time. Summary: ions or neutral molecules which can form coordinate covalent bonds by donating 1 or more pairs of electrons to the metal atom or ion are known as ligands. On the basis of the number of donor atoms present in them, they are classified as monodentate, bidentate, polydentate,
Werner's theory. Coordination complexes were known and studied by chemists from the mid-19th century. However, there was no clue about their structures at that time. In the year 1893, a Swiss chemist, Alfred Werner, proposed the first workable theory of complex ion structures and their formation, known as the Werner's theory. He proposed that in the complex hexaamine cobalt 3 chloride, the CO3 plus ion is surrounded by 6 ammonia molecules